Also good
Hello,
to
and
start.
welcome. I'm Professor Sean Tavalia, Academic Chair for Physical Science at Suffolk Community College and founding member of the board of Hamptons Observatory. For over 20 years now, the Hamptons Observatory has been dedicated to promoting understanding of and appreciation for science through three free quality education programs, such as tonight's event. This event is co-sponsored by Suffolk County Community College's NSF-sponsored iSuccess program, a program that provides scholarships and extracurricular activities for students enrolled in STEM fields. Although this event is free, it could not be possible without the generous donations of people like you. For more information on how you can donate to ensure these programs continue, please visit the Hamptons Observatory website. If tonight's program inspires you, please consider enrolling in one of the many traditional or online astronomy classes at Suffolk County Community College. And again, I always apologize for the plug, but have to do it. During the talk, we ask that you keep your microphones muted. If you have questions, please pop them in the chat. And at the conclusion of the presentation, we'll try to address all questions. So without further ado, tonight's speaker received her PhD in geophysics and space physics from UCLA and is currently a research scientist at the SETI Institute, where she leads the Unistellar Citizen Science Comet program. She currently studies the evolving activity of comets, asteroids, and interstellar visitors using a global network of telescopes operated by citizen astronomers, working to bridge the professional and public astronomy in the exploration of solar system and beyond. Please join me in welcoming Dr. Ariel Graykowski. Ariel, it's all yours.
Thank you so much, Sean. Hi, everyone. Yeah, I'm Ariel, and today I thought it would be fun to talk about some of the research I get to do with the citizen astronomers, specifically of comets and interstellar objects, especially 3I. That's been the funnest object right now. But first, I think I'll start by just talking about our citizen science network. Um, Basically, we're able to have this science program with Unistellar because Unistellar has a partnership with SETI. So I'm a SETI scientist. I do astronomy for the SETI Institute, but they're partnered with Unistellar, which is a French company that sells smart telescopes. So these are some of the models of the smart telescopes. They call them EV scopes, so you might hear me say that throughout the talk as well. But their goal is to sell telescopes, right? So they get to do science with these telescopes because of that partnership. But their other goal is to democratize astronomy. They want to make it really easy for anybody to pick up and learn and do. So basically, you control these smart telescopes through an app on your phone. You turn your telescope on, the telescope will scan the sky, it'll figure out where it is, it'll detect the field. And then from there, you'll see a catalog of objects that you could look at. You click on it, it will turn automatically, point to it, and you can start long exposing. And you can see these really amazing deep sky objects even in the city. So that's like the very fun part of it, the very easy part of it. But our network is pretty large. At this point, we have over 15,000 EV scopes across the whole world. This is just a little animation of how the network has grown just from 2020 to 2023. So it's not even updated, but it's been growing quite significantly where we have telescopes pretty much in every time zone and in both hemispheres. And this makes a really good tool for science. And so, because of that, we have 6 different science campaigns through Unistellar that involve transients, so like supernova, exoplanet transits, occultations, asteroids moving in front of a star, comets, which is the program I'm in charge of, planetary defense, which looks at near Earth asteroid flybys, and satellite surveillance, satellites being the artificial satellites that are being launched more and more all the time, keeping track of those. So there's a lot going on, and having a worldwide network of telescopes makes it really cool to do each of these campaigns. But I am only going to talk about one of the campaigns today, and that's comets. So, comets with Unistellar, our goal with this network is to monitor comets over time. Comets are active bodies, so they have a lot of ices. When the ices warm up, those ices turn into gas. And that is the activity of a comet. And you see that in the form of a coma and a tail, like in this comet here, which was naked eye this fall, actually. This is C 2025 A6 Lemon. And this was taken by one of our citizen astronomers. But what we want to do is we want to observe the comets often and for a long period of time to build what we call secular light curves. These light curves help us model the brightness that we've seen so far and predict how bright it's going to be in the future. And they also help us understand what the activity is doing. Is it more or less active than other comets in similar populations, for example? Also, since we can build up these really comprehensive light curves, just filled very well with data points, we're able to very quickly follow up on a transient event, something ephemeral like when a comet has an outburst, which I'll talk more about later. When people participate in this program, everything that we're working on is listed out very clearly on the website and the app. And you can find predictions based on where you are to tell your telescope where to point. And then if you want, you can upload that science observation to us, and then I would download it and analyze it. But everything, every step of the way is voluntary, right? So whenever anybody uploads a data set, they get a result back within 12 hours of upload with our automatic pipeline. And so there's some challenges of automating a pipeline for comets. The results they get back will be how bright the comet is and kind of how it varied over a short period of time. And then a movie of what you saw and a final picture of what you saw too. But measuring a comet's brightness is hard to do in a universal way. So I'm going to talk about some of the challenges of measuring comet brightness. So I'm using this one as an example. This was another fairly bright comet in the fall this year, 2025 R2 Swan, also taken by a citizen astronomer. But this comet is a really good example of what makes it hard sometimes to do what we call aperture photometry. Aperture photometry is basically taking a circle and putting it over the image right with the target in the middle. And every bit of light that's going through that circle, I can calculate as a flux. I can add all that light up, and that's my flux. I can convert it to a magnitude, essentially. But I need to pick the right size. So, for example, this aperture is too small. I'm missing a lot of the light from the coma of this target. And when I measure, I want to get the total brightness, which includes the nucleus, the object itself, and the coma. But if I go too big, it's starting to get too noisy. Now I'm measuring the flux too much from the background. I'm also measuring a lot of flux from these background stars that are making it into my aperture. And so we try to pick the just right size, right? So this aperture is just right. Or is it? There's actually still some problems here because there's still a lot of background stars getting into this aperture. So for really large comets like this, when they're large on our detector and they're going over a lot of background stars, we try to do things a little more carefully, which is looking at a surface brightness profile. So this is a different comet, but in the same situation. It was big on the detector. There's a lot of background stars. So I don't want to just add up everything in the circle. Basically, I start at the center of the target and I take concentric circles and I go outwards and I take the median within each of those concentric circles. That way, by starting in the middle, I'm ignoring the light from stars. And then I can integrate all the way through where the coma ends, add up that light together. So this is a way we can avoid background stars in big comet situations like this. And so that's what we did for this comet. This is Comet 103P, Hartley 2. This comet is a famous one because it's hyperactive and a spacecraft has visited it. And hyperactive just means it's a small comet, but it's giving off a lot of stuff. Too much stuff. It doesn't seem to have enough surface area to give off that much stuff. But what's happening is it releases chunks amongst that stuff, and those chunks have their own surface area that are also sublimating. So that's how you can end up with something like Hartley 2, a hyperactive comet. And so we did a project with this one where we built a light curve. So we watched it all through its apparition, this time period where we could see it in 2023 to build a light curve. And it looked like this. So this one is actually kind of messy. I'll show you a cleaner light curve later. But it's messy because despite having better techniques, it was still very challenging to get a solid measurement of this object due to how big it was, how many background stars, weather, and stuff like that. But basically, all the data points you see here in blue, all those points came from Unistellar. In red, they came from another citizen science organization called the French Astronomy Association. And then the silver ones are from a database called COBS, where anyone can voluntarily upload their measurements, whatever they get. So there's not really a good control on the instruments they're using or how they're doing the photometry. But with our data, our Unistellar data, mixed with this AFA data that we were collaborating with, we're able to control and do the photometry the same way and understand the instruments that we were using. And for Unistellar, that's a very standardized instrument across the board. So despite the messiness of the data, we can look at just the top because that's where the comet is the brightest. That's where we know we're getting all of the light and we're not missing anything. All the data points below, we probably couldn't make the aperture very big because there was a bright star in the way or something. So that's why we fit this model to the top of the data. And we fit it just to our data, but it happens to match really well with the top of the data submitted to COBS as well. So that was reassuring for us. So we're like, okay, we're building our light curves well, even when the data is messy. And we were curious about how this activity evolved throughout time because this comet has come around a lot. We've observed it 3 other times in the past. And so I can take a look at past data. Now this graph is a lot of data points, a lot of graphs. What you want to know here is just the same graph I just showed you is the one on the bottom. The other 3 on top are light curves from the past, right? So from the 1991 apparition, the 1997, 2010, and then ours from 2023. And I wanted to do this because I wanted to compare how the activity changed year to year. And what we found was that if we look at the peak activity, it decayed over each apparition, each time it came around. So I plotted that. These 4 apparitions are plotted in this pinkish purple color. And there's a very clear trend downward. I fit a linear fit to this downward trend just for simplicity. So you can see it clearly. And also, I wanted to get a guess on, well, if it's going to keep declining in activity, when will it go dormant? When will it have no more ices to sublimate? And that would happen around where that dotted line is, basically where it's the only brightness coming from the comet comes from the nucleus because there's no coma to give us any brightness. That happens at that vertical line. And that would be in 2012, plus or minus 18 years. In reality, this is very conservative, or that'd be the soonest possible time this comet would go dormant, because in reality, we're going to see it taper off in activity much more slowly, and it'll probably be slowly active for a very long time. So that's just to give you an idea of what the trend is looking like right now. It's definitely a clear decline in activity, and actually, because of this decline, it's lost its hyperactive title, which is kind of a big deal. It's a little bit sad. It's like when Pluto became not a planet anymore. But it is what it is. And it's kind of cool that we were able to confirm that thanks to our network of citizen scientists. So here I just wanted to share, this is a bunch of observations that happened over the course of last year, over the course of 2025. And so this includes all of our campaigns. Comets, every time a comet observation was done, that's in green. And so that's what I want to focus on. But I also just wanted to point this out again to show you that our network really is worldwide and they're active and they're observing every day. And it's really useful to build those light curves, but it's also really useful to look at outbursts or ephemeral events. we can really make sure that we're in the right place at the right time when something happens that's happening quickly. And such was the case for the DART mission. For those who don't remember the DART mission, this was a NASA mission that sent a spacecraft to the Didymos Dimorphos asteroid system. It was set to crash into the smaller asteroid of the system, Dimorphos, and it did. The goal, hoping that we can change the momentum of an asteroid by impact, and it was a success. NASA was able to change the orbit of Dimorphos around Didymos, and therefore that means they imparted a momentum change, which is exactly what we need to be able to do perhaps one day. So this was a really successful mission, but when this impact occurred, only a few places on Earth could see it, could take a ground telescope and watch it happen. Even space-based telescopes had a hard time seeing the impact itself. Hubble missed the actual impact because it moves, the asteroid moves relatively quickly, and it was just hard for Hubble to get to it in time and stay on target. So we had to really dig into our network and say, hey, the people who are here, you need to get these observations for us, right? This is very important, not just for us, but for everybody. And so we had people all over the world contribute to this project, but specifically the spots that you see in Africa are what we needed for the moment of impact observation. And so this is a little video of the perspective of the DART spacecraft when it hit Dimorphos. Boom, little loop there. That was a super exciting thing. I remember when we were streaming this, it was very exciting. But this is the perspective from a Unistellar EV scope in Africa or off the Reunion Island off of Africa, actually, this one in particular. And what you're going to see is the asteroid system moving across the sky. That's that dot on the right. I'll play this in a second. You're going to see it moving. We can't distinguish Didymos from Dimorphos from our distance and our resolution. And you're not going to see the DART spacecraft either, but you will see when the impact happens. Right here. So you can see the system gets bright. You see a puff of dust coming off of it and dissipating to the left. And we were very excited to see this. We didn't know what was going to happen at all. And because of this, we were able to build a light curve once again. So this is how that light curve looked. We had a few different observations of impact, so that was really good for us to confirm the timing of impact that NASA reported. But also, when we published this work, we published in Nature in 2023, along with the rest of the DART team, their first papers that reported the results of DART. But we were the only ones who were able to catch the time of impact and publish what we found. And so we were the only ones that were able to report how much mass was lost, which we got 10 million kilograms, which was later corroborated by NASA. We also were able, because we saw this mass loss and we saw the speed at which that mass was lost, we were able to confirm the momentum change that we estimated a momentum change that corroborated what NASA reported. And then finally, we also saw the color redden a little bit right on impact. It got a little bit redder and then it dissipated back to its normal color. And we reported that, and NASA also later corroborated that they had also seen that as well, which they published later. So because of this network, because we can follow up so fast and we can act quickly, or worldwide, we're able to do something very, very cool and be a part of what NASA is doing, which I think people in the network I know really love. But we don't always know when an outburst is going to happen, right? This was a man-made outburst. We're not always going to have that. Usually we don't, especially for comets like this one, 12P Ponsbrook's. So we've observed several outbursting comets with the Unistellar network. This one in particular is one of the most exciting ones, so that's why I picked it. But typically, we don't know a comet outbursted until somebody sees it, right? So somebody else saw it, somebody reports it, and then we can follow up. So Unistellar isn't necessarily discovering outbursts, but we can follow up right away based on notifications. And so there were notifications going around in astronomer forums, but this was also really large in the media because it was such a big outburst. It got 100 times brighter all of a sudden in less than a day. And it also had a funny shape. It looked like the Millennium Falcon, and also people said devil horns as well. And I'll show you that shape. But basically, when I heard about this, I asked the network, hey, we need to get on this right away. And within an hour, somebody was on it. It's nighttime somewhere in our network, and there's always somebody rearing to do observations with their telescope, which is really cool. So right away, they got on it. So we were able to start observing the outburst pretty early on. And the outburst looks something like this. So we have the pre-outburst where it's very faint in the center there. So faint that I didn't know we'd be able to see it at all. I'll talk a little bit more about that. I actually didn't know we had this image until later. But then after the outburst, you could see that this is the object in the very center. It's very bright. The signal is now extremely high. And so that's all this dust and ice and gas coming off of it all of a sudden. And that would slowly spread and dissipate into this shape on the bottom left. This is one, hopefully you can kind of tell this is from our Unistellar EV scopes, that it kind of looks like the Millennium Falcon. There's two little kind of tails there. What people think what was going on is that this shadow that's here is just that it's a shadow, that the coma was casting a shadow, or the nucleus, sorry, was casting a shadow across the coma. So that's kind of interesting, but it made it very exciting to watch and follow, and we could see that shape dissipate and expand as it went on. But this wasn't the first time it had an outburst. It outburst actually a lot. So it was really fun. Once we started observing it, this is a light curve of 12p. We started observing it. Every time it had an outburst, you can see that the Unistellar network was able to monitor every outburst from start to finish, which is very cool and very handy. We can make estimations about mass loss and stuff like that, like we did with the DART mission, but for this comet instead. So this was a very exciting one to follow. But what about before the outburst? What about that image I showed you that we had before the outburst? Well, I didn't really start this campaign amongst our citizen astronomers until the outburst, but a few passionate astronomers did start observing it. They were interested in every new comet that's going on, that's being reported on, or just an apparition of a new comet or of an old comet. So some people actually did observe it. So I was like, okay, I'm gonna take a look. I don't think we're gonna be able to see it because it's gonna be around 17th magnitude. And that's really faint for a small 4.5-inch diameter telescope, which is what the EV scopes are at the max. There's also 3.5-inch, so even smaller. So I really doubted that we would see it, but we did. As I showed you before, this is that image again. It was very faint. The signal to noise ratio is very low, but we did see it, and I was surprised around magnitude 17. And then we watched it go through all its outbursts, and then the image on the right is the same comet, a near perihelion, the next year in March. Obviously, bright and beautiful comet, just to give you an idea of how these things can evolve from little fuzzy dots that you could barely see to something really pretty. But this really made me wonder if we could push this limit. What is the limit for us really, for our EV scopes? And it turns out we can push it. And we pushed it. We got our faintest object on record yet with 3I Atlas. So 3I Atlas is another one that basically when this was discovered, it was very exciting. There was a lot of media buzz. People knew about this pretty much immediately upon discovery. And so we wanted to get on it as quickly as we could. But again, I thought it's closer to 18th magnitude. It's even fainter. I doubt we're going to be able to see this one, but let's just start observing. And amongst the first few observations that rolled in, we found it here. This was taken in a city with the smaller model I was telling you about, a 3.5-inch in diameter telescope. So it was really a lucky observation. A lot of the observations that came in at this time were just too noisy, or the object was probably behind a star. You could see three eyes in a really crowded field when it was discovered. So that made these observations very, very difficult. But we did see it. So we know we could see down to 17.8, basically, around 18th magnitude, with just our small telescopes, thanks to stacking and building up our signal. But this is really important to be able to monitor a comet for as long as we can so we can catch all those outbursts and also just so we can start making those predictions earlier and see what it's doing. So we want to be able to go as faint as possible. This is another just kind of example of the evolution of the of 3I, that with that same discovery, our unistellar discovery image on the left, and then what it looked like after perihelion on the right. Yeah, so a nicely evolved comet. Not quite as pretty as 12P ended up being, but still a beautiful comet, really fun to look at in a small telescope. And we were able to build a very nice light curve for this comet too. So this is our light curve. You can see there's a big gap in the light curve. That's because 3I Atlas was on an orbit that took it behind the sun from our perspective on Earth, which means there was about a month where we couldn't see it at all from the ground. Some NASA solar observatories were able to fill in some of these gaps, which is great, especially because right before we lost it to being behind the sun, there was a little bit of an outburst or some sort of heightened brightening, which I mark by that red vertical line. And so all those dots that are now squares, they mark this heightened, brightened time. But basically, up until then, the data points followed our model very, very well. And so it was on the steady track. It's a very active comet. It's been fun to follow. It's been steady. And then all of a sudden it wasn't steady anymore. And what we think happens here, this was around the water ice line in the solar system, which means probably the water sublimation, the water ice started sublimating into gas. And that gas sublimation just really kicked off here more than we expected it to, which was cool. And we were wondering, did it keep doing that? Is it going crazy or is it fizzling out? What is it doing behind the sun? We can't wait to get it back. And then once we got it back, you can see I have some data points from right after it came back that are very elevated compared to original predictions. So basically, we need to start the prediction over and see how it's doing now. But this elevated activity was occurring while we weren't watching it either, which is cool to know. This is just the legend for that graph, just to show the names of everybody involved, just flashing this very quickly. What we can also do is basically look at the same thing, but in specific wavelengths. So within all the detectors of our telescopes, of unistellar telescopes, is basically a Bayer matrix of red, green, and blue pixels. They're in this blue, green, green, red pattern. And so what I can do is instead of taking the flux from the whole detector, is I take the flux just from the green pixels or just from the blue or just from the red. And so that's what you see here. It's the same light curve, but looking at just those fluxes. And we have to eliminate a lot more data. We can't see as far faint because we're only looking at a fraction now of the flux. And even before, we were struggling with getting enough flux. But we still can build a very solid light curve based on these distinct wavelengths, which is great. But what I really want to know is how the colors change over time. And to do that, we need to compare. So I need to do blue minus V, which is visual greenish, V minus R. And those comparisons, if those change over time, I can see if the comet is getting bluer or redder. And that might indicate more gassy or less gassy, or less dusty, more dusty. Dust reflects sunlight really well in the redder, greener wavelengths. And gas is more sensitive to the blues and ultraviolets as well. And so that's why we might expect a color change as gas turns on. So this is what that is. So B minus V in blue, V minus R in red, and then B minus R, another indice in white. But basically, we see no change at all. And I was kind of disappointed by this at first. But what this is telling me is that this comet is really dusty, as as had already been reported, which is good. Right away, upon discovery, this comet was seen as a very dusty object. It's very red in color, which is indicative of dust, and that dust persisted throughout its orbit. This is pre-perihelion only, so I haven't looked at the colors post-perihelion yet. I'd be very curious to see how that looks. I would expect it to be a little bluer post-perihelion, but we'll see. Something else to note, though, is that these are visible wavelengths, and dust is very reflective of visible wavelengths. If I could look into the UV, I might get a better picture of where that gas turned on. But what I do know is that the dust physics remained very constant throughout the whole orbit, which is expected and kind of cool. I thought it might be fun to go through some observations and misconceptions about 3I just because there's been a lot. And so I'm going to talk about some like other data outside of Unistellar and just go through some of these. There's a lot, so I might not be able to hit every single one, but I think it would be fun to do anyway. So with 3I, one of the first misconceptions happened right when it was discovered. So when it was discovered in the discovery image here on the left, it's faint, but considering how far away it was from the sun, it was pretty bright. And basically, we try to figure out how big things are based on how bright they are and how far they are from the sun. And if all of it, that brightness, if all of that flux is coming from the nucleus, then the nucleus would be large, like tens of kilometers in radius or diameter. So that seemed unlikely, I guess, unfeasible. And so the misconception was that if it is that large and it's that unlikely for such a large object to come wailing through our solar system, then perhaps it's more intentional than otherwise thought, aka an alien spaceship, right? So right away we start with the alien spaceship ideas. But this was a misinterpretation actually from the core because it turned out to be active. The day after it was discovered, the activity was confirmed, and that happened here in this astronomer's telegram. Astronomers have this astronomer's telegram. Seems very outdated, but it's very useful for alerts and stuff like this. So we were able to see, yes, it is indeed active, and it seems to be, we don't know then how active it is, how much coma versus how much nucleus flux are we seeing. And we can't really disentangle that until it gets closer. But even this had some debate. Like from this image, some people still thought that doesn't look active to me. To me, it does, but there was debate. But with Hubble and other spacecraft like SphereX observations, we were able to very soon just confirm this definitely active. In fact, very active. And with the resolution of Hubble, they were able to estimate the nucleus size to be much smaller, to around 2.8 kilometers in radius. Still bigger than the last two interstellar objects that came by, but not crazy, not unheard of, not unprobabilistic at all. Yeah. And then another misconception was piggybacking off what I just said, the fact that it has a coma. So there was the debate, does it or not, at first, but very quickly everyone agreed it does. It does have a coma. But there was still this thought like, well, what if it's still really, really big, but just has a thin coma, right? So what if all that flux really is coming from the nucleus, but and only a little bit is coming from a coma? This could be basically a cloud of a sort of acting as a defense mechanism around a mothership of an alien spacecraft, where if something flies in the zone of the coma, they can detect it and eliminate it, I suppose, you know? But the spherics results were actually really important for this because the spherics results were able to show that 99% of the flux we're seeing is coming, at least, is coming from coma, gas and dust, not from the nucleus itself. And so a thin coma is just not what they saw. What they saw, this is specifically looking at a wavelength, a filter on the left that is sensitive to CO2. And they saw a lot of CO2. You get this bright, bright coma. And they checked in other filters to look for water gas, for example. So when you see this sort of GIF going by, this animation going by, the really, really when the comet's really, really bright, that's the filter with this that's sensitive to CO2. And when you don't see it at all, that's a filter that's more sensitive to water gas. And so they just didn't see much water gas. And that was what was really interesting about the coma. It was very carbon rich. And later, the water gas, the ice did start sublimating. That did turn on. But it's still a very carbon rich coma, which is cool. Interesting. Another kind of fun one was what we talked about earlier too, is the orbit itself. The fact that it went behind the sun was seen a little bit as a strategic maneuver. If it's going to do something, if it's going to send out a probe, if it's going to um, thrust and change its trajectory, the best place to do it is around perihelion. And if they want to do something nefarious, it'd be best if Earth doesn't see it, right? So that was the idea that this has to be an on-purpose maneuver, so that Earth doesn't see whatever the alien spacecraft is going to do, some sort of something intentional, right? But in fact, this is really common for comets. Um, this is on a very extreme orbit, 3i is. But comets in general are on fairly extreme orbits that take them really close to the sun at perihelion, especially for like Oort cloud comets, these long period comets that are coming from very far away. And so just sometimes we're on the wrong side of the sun when they come by. It happens quite often. It's not, there's no evidence for something unnatural here. This is a very natural phenomenon, one that we expect for extreme orbits, which this is definitely on. Non-gravitational forces was another kind of buzz time. Non-gravitational forces are very common in comets, and basically this is anything that gives it a push that isn't gravity. So mostly in the solar system, the sun's gravity controls where everything goes. If something feels a force or if it's perturbed by something, then it's gravity by Jupiter or some other gravitational interaction. But there are non-gravitational forces in the solar system too. There's impacts, so you could get hit by an asteroid or something that can alter your course. DART, for example. But for comets in particular, any active body, what's going on is they're losing mass when they're sublimating their ice. And so if you think about the classic physics problem where you're a perfectly spherical astronaut in space, you're on a spacewalk and you're fixing the Hubble Space Telescope. Imagine this is you. And so you have a tool in your hand, but suddenly you get caught off from your spaceship and you're floating away. What are you going to do? What you're supposed to do is turn away from your spaceship, throw your tool in the opposite direction. That mass leaving that way is going to impart a force on you the opposite way, right? So now you'll float back safely to your space shuttle. So all is well. But that's basically what's going on with comets is they're throwing stuff off of them. And so especially if a comet is doing this asymmetrically, like it has a jet on one side of it, that can really just apply a force that will push the orbit a little bit, change the orbit just a little bit. This happens all the time because comets are active. And this is just what they do, especially when they're really active, and they're most active when they're close to the sun. So there were thoughts that the orbit is changing because of a spaceship thrust, but it's actually a very natural phenomenon that happens all the time, even in asteroids. There's some asteroids that are active, right? And they can do this as well. And there was some sort of at this point, people really want it to be a spaceship, right? And so there was this hedging going on where they were saying, okay, well, maybe we do agree that it's smaller than I thought it was. And if it's small, then for sure we're going to see some non-gravitational forces because it's going to thrust at perihelion. But if it's big, it's still going to try to do something. It's going to, but if it's too big, it would need a lot of force to change its orbit. So maybe what we'll do instead is send out probes, and then we won't see the orbit change at all. So there was this scenario for seeing gravitational forces and not seeing them, still explaining a spaceship. But in fact, that also still explains a comet either way, a natural comet. And so there was that misconception as well. But we did, in fact, end up seeing some non-gravitational forces on this comet. Nothing crazy. We definitely didn't lose it. We're able to monitor it very easily, even after perihelion, after we didn't observe it for a while. And those forces actually kind of helped constrain down the size even more to about a 1 kilometer in diameter, based on one publication, which makes this a very typical sized comet. Very similar in size now to 2I Borisov as well. The anti-tail was a big one, is a big one. The anti-tail is really weird and cool. Anti-tails are basically tails going in the opposite direction that you would expect them to go. So in comets, we expect the tail to be blown in the opposite direction of the sun, essentially. The solar radiation pressure sweeps gas really well and some dust, to push that tail that way. It also, for the dust tail, has something to do with the velocity and trajectory of the comet itself, too. But that sweepage typically keeps an anti-tail from forming. If particles start going towards the sun, they get swept pretty quickly the other way. But that's not the case for this comet. This comet has a physical anti-tail where particles are being ejected towards the sun and they're persisting for a little while. This is rare, but what we already know and that we were able to confirm with our Unistellar network is that this comet is very dusty, and those dust physics just won't quit, even through perihelion. This comet releases more and more dust to keep up with the gas. The gas drags the dust out with it. And what it seems to be is that this dust is prevalent and the particles are big. So if the particles have enough momentum themselves, they can push against the pressure from the sun, the solar radiation. So that's what's going on here. And we have seen this in other comets too, though it's rare. So it's very cool. We do see a non-physical anti-tail in a lot of comets as well. And what I mean by that is it's more of like a trick of the eye. It's a observational geometry thing. You're kind of seeing the tail sweep around itself is how it looks, when you're at a certain angle. So we see that a lot too, but that's not what this is. This is a physical anti-tail. It's very cool. It tells us we got some dusty big particles on our hands, which is interesting. Another one is the detection of a high nickel to iron ratio. So this was interpreted as, oh, there's nickel and iron in the coma. Well, that's not natural. This comet shouldn't have metals in it. It must be made of a nickel iron alloy and therefore be a spaceship made of a nickel iron alloy, right? This one is actually very interesting, but has a natural explanation as well, of course. What was found was a high amount of nickel compared to iron. And we do see nickel and iron in other comets too, and it actually is a big question in the comet field still, how exactly we get nickel and iron into the coma of comets in the first place. There's been a lot of studies about how that evolution happens. How do we get that there? But even so, though we've seen this, when we first started observing 3I, these papers in particular found that that ratio was very different than anything we've seen in our own solar system. Too much nickel per iron. But as the comet got closer to the sun, you could see that that iron level caught up. And so now that ratio, which is plotted in this right graph, that ratio has decreased as it got closer to the sun. And now it's looking in this regard just like any other solar system comet. So it's telling us a lot about the potential mechanisms that can put nickel and iron into the coma in the first place. For example, we know now that nickel seems to be put into the coma at much lower temperatures than iron. And then iron catches up later. And so that tells us that this comet probably formed in a very cold part of its solar system. And so what we want to do is try to compare that to our farthest away comets that have these signatures as well. See if we can understand this evolution a little bit better. But there are theories about what kind of organometallic carbonyl compounds could be holding these and then disintegrating or dissolving and releasing the iron and nickel into the coma. And this is helping answer those questions, which is awesome and cool. And not an alloy, not a spaceship. Okay, so now we want to talk about this sort of gap time. And during this gap time, that when we couldn't observe it on Earth, NASA's solar observatories were able to. And what they saw was, yes, this comet is brighter than it should be still, just as we kind of saw before we lost it. And based on the wavelengths that these instruments were looking in, it's very blue. The comet was very blue at the time when compared to our sun, which in these specific instruments, which didn't observe the comet, like the whole time we were observing, for example. This is just during this perihelion time. So it saw that it was bluer than the sun, which basically means that the comet was really expending a lot of gas, which we already knew had turned on. So it made sense to see that it was very, very blue in color in these specific wavelengths when compared to the sun. But this was misinterpreted as perhaps, oh, it's bluer than the sun. Well, it must be hotter than the sun. It must have its own power source as an alien spaceship. But that's just not how comet colors work. Colors aren't indicative of energy or temperature for comets. They're indicative of composition. So that was just a misinterpretation that got a little bit carried away. But it's very cool because it confirmed basically what we expected is that this gas really kicked it into gear at this time. Okay, this is my last one, and this one's kind of silly. This one just made me go, what the heck? What the heck, you guys? But there was an image that came out on the left of 3i Atlas that happened to have an artificial satellite go straight through it, which is so annoying, right? This is happening more and more in our field. But that's really all it is. It's so annoying. We have so many images of 3i Atlas, it's fine. But this image kind of spread around for a second because it was claimed that, well, this line, I guess it could be a satellite, but also couldn't 3i be finally sending its probes, shooting it straight out like that? Which would just be kind of a very convenient thing. You can also tell it's an artificial satellite because it might be hard to see in this stream, but there's this increase and decrease of brightness throughout the line, throughout that line, which means that satellite is rotating, which we expect. And so sometimes it shines a little bit brighter than other times as it's rotating and moving, orbiting the Earth too. So basically right after this picture was taken, another one showed that the satellite's not there anymore, which indicates that these aren't persistent probes. This was a satellite. And so it's just very easy for this comet in particular, for this object to have a lot of misinterpretations. And this one's just kind of a silly one, but just a warning to just be aware that people want this to be a spaceship so bad, but the evidence is so important to follow, and not setting up fallacies ahead of time, but looking at the evidence first. And then I just put another set of pictures of a bunch of satellites, not going straight through the nucleus, but going through the tail and still being very annoying, an increasing problem in our field of astronomy. Okay, I'm going to wrap up pretty quickly. I have a couple more things I want to say. this is just, again, all the things that we were able to do with Unistellar with 3i. We looked at the color over time, the brightness over time. We're really been able to watch this evolve and corroborate a lot of the findings I told you about through our own data. And also, like with the DART mission, I know our citizen astronomers really enjoy being able to see for themselves and participate in science like this. I want to talk a little bit about how you can get involved, how people can get more involved in citizen astronomy. Basically, there's more and more astronomers coming along all the time. This just kind of shows you the age of different revolutions of astronomy that really kind of kicked people into wanting to do astronomy and the exponential growth that we're seeing from Copernicus to Sagan to the exoplanet era, and now what we're calling the survey era with the now Vera C. Rubin observatories online. A survey telescope like this is going to discover so many things. It's going to be hard to keep up with. But with networks and that we have with citizen astronomers that can use their at-home telescope in an easy way, we can keep up with this survey era and basically also expand astronomy to not just professionals, but to amateurs as well, but invite them into science in the professional setting. And with that, there could be millions of us. And we like to pose the question, what if you could map the sky, all of the sky, all of the time, to really harness that power of a global network, which is what we try to do with Unistellar. But actually with SkyMapper, this is a new venture my team is working on, is taking this concept to the next level. And they want to utilize decentralized science to do it. So they want to keep things open and transparent and on the blockchain so that way data is shareable and not fudgeable. They want to utilize decentralized physical infrastructure, which we already do with Unistellar, but the hardware would essentially be owned by the user and spread around the world. With SkyMapper in particular, you can hook up your telescope with their hardware that they call a sky bridge so that other people can use it. And that will really expand what we value a lot in my group, which is networking science, which I've talked about a ton. And this is just a quick little example of how the SkyViewer SkyMapper platform works. Essentially, you would log on to this platform, you would pick a telescope that's available somewhere in the world, somebody that has a sky bridge, and now you can control their telescope. And you could do a science observation. You could do an observation for fun. You could use it for teaching or outreach or whatever. Or again, comets, and then upload your data, and we will do on a much grander scale these same sorts of studies. And also not just with comets, but all sorts of science campaigns that I showed you earlier. I'm gonna just skip through this a little bit. Oh, I do want to show actually. Okay, so then this is where like the telescope gets on a target and now it starts to expose and you'll see that this nebula becomes brighter and brighter, which is kind of cool. So again, use it for fun, use it for sky viewing, use it to look at the sky when it's daytime in your area, or use it to contribute to science. So this is kind of how it would work. So with that, I'm going to leave this up as my summary slide. This is the rest of my team. And so we're doing all sorts of stuff, not just comets. And if you're interested in any of those, I definitely suggest reaching out to these people, especially if you're interested in SkyMapper and expanding this network and making it more accessible. And it's not just going to be unistellar telescopes with SkyMapper. It's going to be all kinds of smart telescopes alike. And so I'm very excited to get more and more data and keep up with this survey era of astronomy. And with that, I'll take any questions.
Thank you, Ariel. That was fascinating.
Thank you.
Yeah, as someone who has spent years, using the old-fashioned telescopes,
Yeah,
we always kind of lamented about the new telescopes that made it so easy.
totally.
In great ways that it brings it to the regular people out there, but there's something missing. But now, the presentation you gave, I never really thought of the possibilities of what it created.
Yeah, I'm really glad
And
to hear that. I mean, there's so much value in learning how to use a telescope and using one.
Yep.
it feels good. It's awesome, and you learn so much. But like as a scientist on the other side of this, I really like getting a ton of data all the time, and I love talking to our citizen astronomers who are like, I can't believe I was on a Nature paper, because they're all co-authors when we publish something.
Yeah. And
Yeah.
don't get me wrong, I love going out and setting mine up and letting it
Yeah.
do its thing.
Yeah,
But
yeah, yeah. Oh
it's
yeah.
very,
You could go inside, you can relax.
so there's one question in the chat from Kai. You're much calmer about these, but what if it's aliens? People.
Yeah, well, if it's aliens, that'd be great. I work for the SETI Institute. All we want to do is find aliens. I would love to. I'd be paid for life, funding forever.
So what are some of the other possibilities now that you've been doing this and looking at, just through your lens, what other possibilities do you see from the citizen science standpoint?
Oh, that's a good question. Well, something I do really want to do with the Unistellar network that I think is going to be made easier with expanding to SkyMapper is discovery. So I would really like a comet to be named C2026 A2 parentheses Unistellar, right? I think that we're really well equipped to be looking at the sky all the time. We should be able to find these little moving bodies for the first time. And we're looking in areas that like Vera C. Rubin can't see because we're worldwide. And Vera C. Rubin is going to outdo us no matter what in discovery, but it's limited to the southern hemisphere. And we have a lot of telescopes in the northern hemisphere. So I'd really like to start a discovery and automated alert system. So when there is a new discovery, we could follow up right away to confirm. And this would go for outbursts as well. We want to discover those outbursts. We want to tell everybody because a lot of these outbursts aren't as exciting as 12P and they go missed. And so I'd like to automatically just keep track of these and follow up on them more often by finding them and alerting automatically.
So in terms of the network, what was the biggest barrier?
Well, sometimes it's language.
Mhm.
So we work together on a Slack platform with our citizen astronomers. If you want to become a citizen astronomer, you can just join the Slack.
Yep.
And sometimes people ask us questions in another language, and we have Google Translate, which has gotten pretty good,
Yep.
but still sometimes it's like I'm not exactly sure what they're asking and stuff like that. And so we're trying to communicate as best as possible with people all around the world. There's also a barrier in cost, right? So these telescopes, the unistellar telescopes, aren't necessarily cheap. So our science team does have programs where we donate telescopes to community college teachers and to 4-H clubs and stuff like that. We try to do that when we can to overcome that barrier as well, because those are the people we really want to have it and to be participating.
So David wants to know what is your hope for how the citizen science could contribute in the next 20 years with better tech, right? As that's coming along. That's
Yeah, no, true. I mean, I think we're going to see these smart telescopes get bigger, for one. This first couple of generations of smart telescopes, not just for Unistellar, but for everybody making them, have been on the smaller side because that makes them really portable. But now I think we're getting a lot of people interested in the science side of it, and having a larger telescope will let us see fainter. And I'm seeing these companies make larger models in the last year or two. So I'm really excited about that. I think, yeah, technology is going to get better. People are going to be more well equipped to use these scopes and to want a bigger one, and then they could take their little one on a camping trip or something, but maybe station a larger one at their house.
Yeah, I can't imagine just going back from the days of the old CCD cameras to the new
I
CMOS chips,
I know.
right? I can't imagine what a CMOS chip on a 20-inch telescope compared to the 3 inch is going to just the resolution is going to be incredible in
It's
terms of
going to be
yeah.
incredible. And also, right now, we don't use any filters.
Mhm.
Unistellar doesn't, but I know Celestron does. And I think that'll be a really cool thing too. Instead of me having to divide up the flux on
Yeah.
those RGB detectors, to use an actual filter will be really cool. And I think that'll become more in vogue as the tech gets better too.
Yeah.
Yeah.
Well, this was wonderful. We really appreciate it, and
Yeah, thank
clearly so
you.
does the audience. And hope you enjoyed being with us for the evening.
Yeah, I really did. Thank you so much for having me. This was fun.
Yeah, we look forward to maybe having you back in the future. It'd be wonderful
Yeah, definitely.
with
Thank
the
you.
next discoveries, right? And all the
Yes.
good news that you bring us.
Yes, yes, yes.
Well, thank you again for your time, Ariel. And like I said, we really appreciate everything you're doing, everything that SETI does, and look forward to what's to come.
Thank you so much, Sean.
Have a wonderful evening. Thank
You
you,
too.
everyone, for joining us.
Bye-bye.